All right, guys, Mr. Antonucci, and this is the last part of section 8A and part 5 here. Perform a chi-squared test for goodness of fit. So this is the appropriate inference for procedure for testing a claim about the distribution of a categorical variable. We call it the chi-squared test for goodness of fit. This is a significance test of the null hypothesis that a categorical variable has a specified distribution in the population of interest. So our example here, many people loved the tree-lined streets, especially in big cities where tall buildings can dominate the landscape. Are trees in New York City streets proportionally distributed across the 5 boroughs? That is, if a borough has 30% of the land area, does it also contain 30% of the street trees? This table shows the land area for each borough, each of the 5 boroughs here, along with the borough's percentage of total area, as well as the number of trees from a random sample of 1,000 trees in New York City streets. So, two things. We're going to do a 4-step process for a significance test here. And then we're going to see what kind of error we could have made in part A and explain that. So remember, if we're trying to look for convincing evidence that the trees on New York City streets are not proportionally distributed across the 5 boroughs, we would need to perform a full significance test and follow the 4 steps. Okay, so the first thing always is the state step. We're going to state our null and alternative hypothesis and the significance level. So our null is that the trees on New York City streets are proportionally distributed across the 5 boroughs. And the alternative is that the trees on New York City streets are not proportionally distributed across the 5 boroughs, and we're going to use a significance level of 0.05. Now, the plan step, remember, the first thing you do is you want to state the procedure you're using before you check the conditions for it. So we are performing a chi-squared test for goodness of fit. So we have to check the 3 conditions, random. Again, you have to actually check it. You have to write a sentence here. You can't just write the word random and put a check mark. It's not going to earn credit. So the data came from a random sample of trees on New York City streets. 10%, again, can't just put a check mark, have to write a sentence. So we must assume that 1,000, that was our sample size, is less than 10% of all trees on New York City streets, which is reasonable. New York City is an enormous city. And then we need to check then we need to get the large count condition, which we need to calculate the expected counts. Now here, we just multiply the sample size, 1,000, times the expected proportion for each borough. So if we look back up here, we have the area percentage. So for example, Bronx will be 0.1404. Multiply that by 1,000, and we get 140.4. Okay, so we do that for all 5 boroughs, and they're all greater than or equal to 5. Okay, this is going to suggest there's some evidence for the alternative because the observed counts are different than the expected counts. Okay, so like 140.4 is different than 123 of our observed counts. Okay, which is not really that surprising, but we want to know, is this difference significant or not? So in our do step, we have to calculate our chi-square test statistic. So here we would have 5 terms. You could do this by hand, or you could use your calculator to calculate the chi-square test statistic of 15.5. Now, our p-value is going to have degrees of freedom of 5 minus 1, which is 4. From the calculator, our p-value would be 0.004 degrees of freedom. So what I have here, I'm listing the chi-square, the p-value, and the degrees of freedom. Make sure you have at least that on your paper if this were a open-ended free response type question. Also, it would be helpful to write out the first couple of terms for the chi-square test statistic, and then you can write out like 2 or 3 of them and then put plus ... and that would be sufficient for showing the work there. Okay. If you had used the table, you'd get a value between 0.0025 and 0.005. Here's a graph of our chi-square with 4 degrees of freedom. Chi-square of 15.15 would be right here. And we want the probability of getting a value that large or larger. Okay, so it's 0.0044. Now, our conclusion, because a p-value of 0.0044 is less than our significance level, we reject the null. We have convincing evidence that trees on New York City streets are not proportionally distributed across the 5 boroughs. Okay. And then part B, we wanted to know which type of error, type 1 or type 2, and explain our answer. Well, since we rejected the null for our conclusion, that could have been an error. That's a type 1 error. We found convincing evidence that the trees on New York City streets are not proportionally distributed across the 5 boroughs, but in reality, they could be proportionally distributed. All right. So that doesn't mean we did commit a type 1 error, but if we did, that's what the consequence would be, or that's what the error would be in that case. Okay. So when we talk about um, chi-square test statistics, and we looked at this example where we had the calculator back here, and it talked about the contribution rate here. This is where we want to talk about this for this one. So here we have a table that shows the observed, the expected, the differences, and the contributions for the chi-square test statistic for New York City streets. So we have our borough observed, expected, the difference, and the contribution. So that would be the individual things that you added together in the chi-square test statistic. So you can see here that the two biggest contributors came from Queens, with 2.54 and Staten Island 8.07. In Queens, there were 30.3 more trees than expected, but in Staten Island, there were 39.3 fewer trees than expected. So those were the biggest contributors, and that's how we do a little bit of follow-up analysis. All right, guys, that's it for this one. Hope that was helpful to you. Reach out if you have some questions.